This picture is from 3.1, but I want you, it's on page 117 in your book if you want to screenshot it from your book. Otherwise, you can take a picture of this screen. But I want to explain what happens to the mean, median, and mode depending on the shape of the distribution. And it's important to understand. Okay, in this symmetric one, where we've got similar shape on either side, notice that the mean, median, and mode are all lined up in the center. Okay, so if I have a symmetrical distribution, using the mean, median, or mode will all be very good ways to tell about what's happening with the data. In a right skewed or positively skewed set of data, the data is shifted to the left and the mean is going to be to the right. So on a right skewed distribution, the mean is going to be to the right of the mode and the median, which means it's going to be higher. Okay, it's going to be a bigger number. The opposite is true for a negatively skewed or left skewed graph. Okay, the median and the mode are going to be to the right, and the mean will be to the left of the bulk of the data. The bulk of the data is over here, but the mean will still be in the middle. Okay, so it will be to the left of most of the data, and this is going to be important to think about when you're trying to decide which measure of central tendency you want to use. And the shape of the data has an impact on that. That's one thing we didn't talk about in 3.1 and I wanted to get to. All right. One of the things that comes up in life, people say, oh, you can't compare apples to oranges. Those are apples and oranges. You hear that phrase all the time, which is, it's a silly phrase, but whatever. I'm like, yeah, they're all fruit, but okay. But one of the things that we can do with statistics, even though when I have a data set of apples and a data set of oranges, I can make comparisons about those different sets of data in terms of their variability and how spread out the data is. Even though I might not be able to compare the apple to the orange, I can talk about its spread of the data. And what we do is we use the coefficient of variation to do that. Okay, we compare the standard deviations for lists that consist of different variables. So the different variables being apples and another being oranges. And we can use the coefficient of variation to make a comparison between those two different sets of data. I'm going to put two formulas up because one is for sample and one is for population. But the reality is it's essentially the same formula. I will tell you that we always express the coefficient of variation as a percent. Okay, it's expressed as a percent. There's going to be a formula for sample. There's going to be a formula for population. And I will write in between what the generalized formula is, regardless of if you have a sample or population. Here's sample and population. And so we write this coefficient of variation with the little c and then var. Okay, here's all that this is. This is the standard, the standard deviation over the mean. You have the notation for sample, which is the s over the x bar. For population, you have the lowercase sigma over lowercase mu. All right? It's just the standard deviation over the mean. So, take a picture of this problem, and we will talk through and do it. So what are the two things that we're making comparisons of? What are the apples and oranges in this case? Sales of cars and commissions. Okay, do you guys know what commissions are?
Yes.
What is it?
You make a certain percentage on how many you sell.
Percentage of sales, yep. Yep. Percentage of the sales that the salesperson earns. Okay? So, standard deviation over mean. So, for the number of car sales, okay, those are my two comparisons, right? I'm doing sales and commission. Go ahead and find the coefficient of variations for each of those. Go. So here's what you had. Okay, coefficient of variation for sales. The standard deviation is 5. The mean is 87 for commission, the standard deviation was 773, and the commissions were 5,225. How many have them set up like that? Okay, good. Convert them to cents. So for sales, the coefficient of variation is 5.7. For commissions, it's 14.8. What's my conclusion? Which one is more variable? Sales or commission? Commission is more variable, and here's what it means. Okay, commissions are more variable than sales. If I had all the data for commissions, which I don't have, they only gave us the standard deviation and the mean. But if I had a list of all the commissions at this particular dealership, what it would be saying is that the data for commissions would be more spread out than the data for sales. Okay, the number of cars sold. Those numbers would change. Okay, and the numbers for sales of number of cars sold will be bunched closer together than that of commissions. Okay, that's coefficient of variation. Next, we need to talk about Chebyshev's theorem. Chebyshev is an old dead Russian mathematician, and he came up with a theorem that tells us about how closely bunched data is around the mean. About the mean, okay? That's what's going on in this section. Okay? Chebyshev's theorem. And then I'm going to put it on the screen, and you can take a picture of this screen, and I'll explain what it all means. There it is. The theorem that he came up with tells us about the proportion of the values of the data set. So what percentage of the data set is going to lie within K standard deviations? Okay. K does not necessarily have to be an integer, number of standard deviations. What we talked about on Friday was how to find the standard deviation. Today we're going to talk about number of standard deviations away from the mean. And the distance away from the mean is one standard deviation. And so for each particular problem, one standard deviation, two standard deviations. That the standard deviation for the problem will tell you how far away from the mean you actually are. This formula 1 minus 1 over k squared is what's going to actually be most important. So here's the first part. At least 75% of all the data. So at least 3/4 of all the data is going to be in between the two standard deviations of the mean. Meaning 2 standard deviations above the mean, 2 standard deviations below the mean. And so at most 25% is outside of that. Most of the time it's actually going to be a little bit less than 25% outside of 2 standard deviations. And I've got some visual representations of this that you're going to see today too that might help you understand how this all works together. Here's why it's 75%. So what we're saying here is k equals 2. Okay? 2 standard deviations. So I plug 2 into the formula. What's 1 over 2 squared? 1 over 2 squared. What is that? What is this? 1/4. This is 1/4. So what's 1 minus 1/4? 0.75. 3/4. 75%. Okay? That's why 75% of the data, at least 75% of the data, lies within 2 standard deviations because of this formula. So the bulk of the data surrounding the mean is within 2 standard deviations, 75%. Now, if I said this, if we wanted to expand that and go 3 standard deviations away, okay, what I would find is that 88.9% of all the data, at least 88.9% of the data, is in between 3 standard deviations of the mean, because if k equals 3, just substitute in the formula and that's what you're going to get. Like I said, I'm going to show you a visual representation of all this here in a minute so you get a better idea of when I say 2 standard deviations away from the mean, 3 standard deviations away from the mean, what exactly that means. Alright, so let's say for example, okay, the mean of some data set is 65 and the standard deviation is 7. Okay. So 1 standard deviation away from the mean, above the mean, is going to be what? How far away is one standard deviation above the mean? What is one standard deviation equal to in this problem? Alright. One standard deviation is equal to how much?
7.
7. So if I went one standard deviation above the mean, where would I land? 72. 7 above 65 is 72. So if I went one standard deviation below the mean, where would I land?
58.
58. Okay. So what's 2 standard deviations above 65?
79.
79. How'd you get that?
14.
14 plus 65. So 2 standard deviations above 65 is 79. Because one standard deviation is 7, 2 standard deviations is 14. So what's 2 standard deviations below 65? 51. So I subtract 14. Okay? What this means is that at least 75% of the data is in between 51 and 79. Okay? Because of Chebyshev's theorem that says 2 standard deviations away from the mean, at least 75% of the data is there, I can actually say that if I, even without having all the data, I know that at least 75% of all the data in this set is going to be in between 51 and 79. Which means at most, 25% of the data lies that's less than 51, and 25% is greater than 79. So combined, the number of data values less than 51 and the number of data values greater than 79 can at most be 25% of the data. 75% of it needs to be in between there. So here's a visual. You can take a picture of this. Now, what this graph represents is that this is the mean here in the middle, okay? And if you noticed on the very first page of these notes, the mean was always in the middle of the graph, okay? 2 standard deviations. This is 2 standard deviations below. Okay, that's x minus 2s. And then 2 standard deviations above. As a visual, at least 75% of all the data has to fall in there. Okay, that's what that's saying. That's what Chebyshev's theorem states. Okay. If I go out to 3 standard deviations, either above or below, now I've increased it to 88.9% of the data is in between those red lines. At least 75% of the data is in between the blue lines. So it would make sense that the further I move away from the mean, the more of the data is going to be contained within there. Okay? And that, again, on the bottom you see plus 2s. This means plus 2 standard deviations or above. This means below or minus 2 standard deviations. Okay? Take a picture of this page. This problem, they're telling us that the mean is 25 cents a mile. The standard deviation is 2 cents. And what we're trying to figure out is what's the minimum percentage that can lie in between 20 cents and 30 cents. In order to do that, we need to know what the standard deviation, the number of standard deviations away from the mean, 20 cents and 30 cents is. Okay? So here's what we're really trying to do, and I'll kind of give you a visual. So what I have here on one side is 20 cents. On the other side I have 30 cents. The mean is 25 cents. I need to figure out the number of standard deviations away from the mean 30 cents is, or 20 cents is. I could do this one too. This is what we need to know. If we can figure out how many standard deviations away from the mean that is, then I have my k value. If I have my k value, I can plug it into Chebyshev's theorem and tell you the percentage. Okay? Now, the problem here is trying to figure out how many standard deviations away it is. I mean, we can say how many cents away is it. How many cents away is 30 cents from 25 cents? 5 cents. So what I need to know is how many standard deviations does that 5 cents represent? Okay? How would I figure that out? Well, I know what one standard deviation is, right? How much is one standard deviation? 2 cents. So if I'm 5 cents away and I need to know how many standard deviations away I am, what should I do? Say it again. 5 divided by 2. Okay, or in this case, all right, and this is everything that I just said, so maybe you can write that down so you've got kind of a recipe on how to do this. Difference between the mean and the upper value is 5 cents. We need to find out how many standard deviations away from the mean that is. And that's what we were just talking about. But there it is written out for you. Okay, so we just take that 5 cents divided by 2 cents. So what is that? What's 5 divided by 2? 2.5. Okay, that's 2.5. So what does 2.5 represent? What does that equal to? K, which means 30 cents is 2.5 standard deviations away from the mean. Okay, that equals K. And if I have K, I can plug it into the formula and just simplify it. So do that. Plug that into Chebyshev's theorem and see what you get as a percent. So here's what you should have gotten. Is that the minimum amount of data in between 20 cents is 84%. Okay? So at least 84% of the data is going to be in between 20 and 30 cents. So in this little survey of companies with their mileage allowance, most of the companies are giving between 20 and 30 cents worth a mile for mileage. Some of them are giving less than 20 cents. Some of them are giving more. And at most, 16% of those companies that were surveyed are giving less or more. Only 16%. It's probably less than that because at least 85%, 84% of the companies are between 20 and 30 cents a mile. Okay? That's the information they're giving us. A couple other things that we need to talk about. Okay? Chebyshev's theorem works for any shape of the distribution. Doesn't matter which one, and it always can apply, whether it's a positively skewed, right skewed, left skewed, negative skewed. Okay? The key is that it's at least a certain percentage. One of the things that happens when we have a perfectly bell-shaped curve is we get a different type of distribution. We get different types of numbers that go within one standard deviation, within two standard deviations. This perfectly bell-shaped distribution, or sometimes called a normal distribution, and we're going to talk about normal distribution later on in this semester. It makes up what's called the empirical rule. And when we have a normal distribution, a perfectly bell-shaped distribution, and we have the empirical rule situation, then we can tell you exactly the percentage of the data that falls within one standard deviation, two standard deviations, and three standard deviations. And it's going to look like this. If you want to take a picture of this page, you may. So when I have a perfectly bell-shaped curve or distribution, and we're using the empirical rule, within one standard deviation, 68% of the data is going to lie. Within two standard deviations, it's now 95% of the data. So when we said at least 75% for any distribution, now when we have the empirical rule, 95% of the data is within two standard deviations. and then 99.7. So almost all the data is going to fall within 3 standard deviations if it's a perfectly bell-shaped curve or perfectly bell-shaped distribution. Okay, so let me show you 2 visual representations of that. There's this one, which is okay. All right. Notice that 68% aligns with plus or minus 1 standard deviation. 95% aligns with plus or minus 2 standard deviations, and 99.7% falls within 3 standard deviations. Okay, I actually like the next one better. I like this one better because most of the time when we have a bell shape, it's a curve. I'm going to add some lines up on this. So 95% is there with those blue lines. Let's see. Duplicate. So within 2 standard deviations, okay, I've got 95% of the data. Within 1 standard deviation, I've got 68% of the data. Okay. So that's kind of what's going on in this distribution. Okay. Again, when I say above by 1 standard deviation, that's plus 1s. Plus 2s is 2 standard deviations above the mean. Okay. So again, what all of this is telling us is where the bulk of the data is, and where it is with respect to the mean. Okay.